Quantum mechanics. The pieces were now in place for a way to rationalize all these seemingly contradictory wave and particle behaviors of light and matter. But first, another weird observation. A driving force behind physics has been the criticality of making accurate measurements of physical phenomena and making predictions based on these measurements. This still holds true for quantum physics, but with a twist. There are times when the more accurate a measurement that you make of one quantity, the less accurate a measurement you can make of a complementary quantity. This is expressed in the Heisenberg uncertainty principle published by Walter Heisenberg in 1927. The first two quantities that cannot both be measured precisely at the same time are momentum and position. The more accurately that momentum can be observed, the less sure you are of where the particle, whether it's a photon, electron, neutron, etc., is located. This imprecision or uncertainty is represented by delta px for momentum in the x direction and delta x for the position in the x direction. Here's the equation. H is Planck's constant, and sometimes you might see it written as this, h bar over 2, where h bar is equal to 2 pi. Planck's constant sets the limit for how accurate the measurements of momentum and position can be at the same time. This equation also works at our level, where we measure, for example, the position of cars and their momenta. If that's the case, and it is, why do we feel we can very accurately measure everything we need to know about a car's size and its momentum? Because Planck's constant is so very small. So here's Planck's constant. So here's the uncertainty principle. So if we measure a car's position with a precision of delta x is 1 millimeter, which we could probably do, I'll be able to find its momentum to a precision of, well, delta px has to be greater than or equal to h over 4 pi delta x. Substitute in Planck's constant. Here's our uncertainty in measuring where the car is. And we'll find that we can measure the momentum to an uncertainty of 5.28 times 10 to the minus 32nd kilogram meters per second. We certainly don't have any instruments that can measure a car's momentum that precisely, so we don't feel any restriction from the uncertainty principle. This expression helps explain why electrons remain in their orbits and do not spiral down to collapse into the nucleus. Niels Bohr theorized that if an electron is in a quantized orbit, it does not radiate electromagnetic waves, so it does not lose energy. Heisenberg's principle states that as delta r gets very small, then delta pr gets very large. Now what happened here? What happened to the x? Well, now instead of measuring in x and y coordinates, we're going to measure using r there. So as the distance, the uncertainty in the distance gets very small, then the momentum, the uncertainty in the momentum gets very large. This principle works with any distance. In this case, we're using r for the radius of the orbit, like we showed right there. As the electron moves closer to the nucleus, its uncertainty in position will decrease greatly, causing the uncertainty in its momentum to get very large. This larger momentum prevents it from getting any closer. Picture as you squeeze the electron down, it starts moving faster and faster and faster, until it has so much energy it leaves. And once again, we know that doesn't happen. There's another version of the uncertainty principle, which relates the uncertainty in energy and in time. Fortunately, for physicists making measurements at levels that we can all see, this principle does not affect those measurements due to the very small value of Planck's constant. A car moving down the road has an uncertainty in its position of 1 millimeter. How precise can you measure the car's momentum? We're given delta x over here, 1 millimeter, which we convert to meters, 1 times 10 to the minus 3 meters. Here's the uncertainty principle. We solve for delta px by dividing both sides by delta x. Substitute in our givens. There's Planck's constant, there's 4 pi, and here's the uncertainty in measurement of the position. We get an uncertainty in the momentum of being greater than or equal to 5.28 times 10 to the minus 32nd kilogram meters per second. In 1926, to explain the seeming contradictions between particle and wave behavior and the impossibility of measuring certain quantities simultaneously with perfect accuracy, Schrodinger developed the idea using wave mechanics to describe the behavior of very small particles. Significant work was also done by Paul Dirac, and they shared the Nobel Prize for Physics in 1933. In classical physics, or Newtonian physics, if all the forces on an object are known, all other quantities such as position, momentum, acceleration, etc. can be found. And in classical physics, we've always assumed we can measure things to an incredible precision and then predict exactly what is going to happen. Things act very differently at the very small level of atoms. We've got light being described as a wave and a particle, we have electrons being described as a wave and a particle, and we have Heisenberg telling us that there is a limit to how precisely we can measure position, momentum, energy, and time. Schrodinger conceived the idea of the wave function, which could describe a particle's characteristics like position, energy, momentum, etc. However, with his new wave mechanics, the major difference is you can only find the probabilities of a particle's position, energy, momentum, etc. The key word is probability, not exact. An example of the use of the wave function is in the double slit experiment for electrons. Young's experiment using monochromatic light incident upon two slits showed a unique interference pattern. Electrons showed the same pattern. This leads to a key property of the wave function. It is used to represent all the knowledge we have about an electron in this case. And if a stream of electrons are incident on the double slits, the wave functions of each particle will interfere with the other particle's wave functions. Thus, the interference patterns are explained by analyzing the wave functions and their interactions. Not every function makes a good wave function. In order to be a successful wave function, it has to be a solution to Schrodinger's wave equation. Don't worry about this at all. This is just showing off how pretty equations become when you get to higher level physics. Psi of RT, it's a function of position and time, is the wave function. That's called psi. Squaring the wave function gives a probability distribution. This tells you the probability of finding a particle at any location r at any time. Now, this is only the one-dimensional wave equation. Imagine solving it in 3 dimensions. Understanding the wave function tells you everything there is to know about the particle. But this is college-level physics, even beyond AP. But at least you can say you've seen Schrodinger's wave equation. The solutions to the wave equation show how the periodic table, electron orbitals, atoms, molecules, and chemical bonds work. It describes the world at the atomic level and, of course, the subatomic level, which is so different and counterintuitive to what we see at our level. The uncertainty and probability concepts contradict what can be seen at the macroscopic level, where we know pretty much exactly where things are and how they're moving. But that's how nature works. Quantum mechanics is very different from classical physics. For example, you can predict what a lot of electrons will do on average, but you have no idea what any individual electron will do. It's also different that there is a limit to how precisely we can measure phenomena. But it accurately matches experimental observations, and it predicts other effects which are then verified by experimentation, which is the hallmark of a successful theory. In chemistry, you'll be using the solutions to Schrodinger's equation and the physics you've learned this year to explore the nature of matter.